Hello, pre-calc people. This is the first part of the 12.4 notes. It's going to cover the first 2 pages, and then I decided, so it's not such a long video, the second one will cover the scalar product. Okay? So there are 2 ways that we can multiply 2 vectors together, and we're going to look at one of those ways today. And even though I'm giving you a formula, there's another PDF on the School Loop, and I'm going to go over it in class, but you can look at it, it's up on School Loop, that shows why it's a derivation of these methods that we're going to go over today, because I'm not always comfortable with just giving you a formula. So the other, it uses law of cosines and some substitution, and shows how or where these 2 formulas come from, okay? But for our purposes right now, I'm just going to introduce the dot product. So, the dot product, it is a way of multiplying 2 vectors when they are tail to tail, okay? So this is going to be method 1 of the dot product. The result of a dot product is always a number, which is why we call it a scalar product. And later on, you will see when we look at the second way of doing a dot product, it also is called the inner product. So these all mean the same thing, the dot product, the scalar product, or the inner product. And the way you would do it is as follows. So we read this as A dot B. So A dot B is the product of the magnitude of the 2 vectors times the cosine of the angle that is between them. Okay, so what happens is that gives you the dot product. And again, what the dot product represents is going to come out in a little bit. Like I said, it is a way of multiplying 2 vectors, but we're going to just first work on using the dot product. Okay, so it's actually quite easy. So you're going to, if I have these 2 vectors up here, A and B, and I want to find A dot B, I just go, since I know their magnitude, 5 times 7 times the cosine of 40 degrees, and when we work that out, you will get 26.812. Since the cosine of an acute angle is positive, the dot product will be positive there. Here, B, I have the dot product of A dot B. In this example, it's going to be A dot B. Again, 5 times 7, which is 35, times the cosine of 110. Notice now I'm taking the cosine of an obtuse angle, so your answer is negative 11.971. So what do you notice about the dot product when theta is acute versus when it is obtuse? When it is acute, you're going to get a positive dot product, and when theta is obtuse, you will get a negative dot product. Okay, this is helpful when you don't know necessarily about the angle, but you know the result of the dot product. It kind of tells you something about the angle between the 2 vectors. So what would theta equal if the dot product were 0? So in other words, what would the angle have to be? So we think about the cosine of theta equals 0. That means that theta is going to equal 90 degrees. So what that means is if you get a dot product that equals 0, you have 2 vectors that are perpendicular. And we're going to start to get a lot of different names for that. It's also going to be orthogonal or normal, but you can just go with perpendicular for right now. And what if theta equals 0? What would the dot product be? Well, since we know cosine of, what if theta were equal? So cosine of 0 is 1. That means the dot product will end up just being the product of the magnitudes, because you'd be multiplying by 1. Okay, so in summary, the 3 cases when you're taking a dot product. Case 1, the 2 vectors are going in the same direction. If you think of this as force, it's kind of like the two vectors are helping each other, so the result is going to be, in this case, we still have 5 times 7, so it's going to be 35 times the cosine of 0, which is 1. So the result is just the product of the magnitudes. If the two vectors are going in opposite directions, they're working against each other, so it kind of makes sense that here what's going to happen, we have 35 times the cosine of 180, which is -1. You're going to get -35. Notice I'm always getting a scalar when I take my dot product. And then the last case that we just talked about, if your theta is 90, it's 35 times the cosine of 90, which is going to give me 0. So when the result is 0, you know that the two vectors are going to be orthogonal, which is just a fancy word of saying they're going to be perpendicular. Okay? Okay, what we did on the previous page was when the two vectors were tail to tail, and you saw that the result, the dot product, gave you a scalar. On this page, we're going to look at finding the dot product in terms of finding what I would call the inner product, and that's because what's going to come to you is in its component parts, in its IJK form. So the way this works is you're going to multiply the x coefficients together, the y coefficients together, the z coefficients together, then you add all the three sums and you get your dot product. So in other words, here's a and b. So a is x1, y1, z1, b is x2, y2, z2. The dot product is going to be the product of the x components, the product of the y components, the product of the z components, and then you add them all together. Notice you will still, once again, get a scalar. Later on, we'll look at when you multiply vectors to get another vector. That will be the cross product. Okay, so how do we do this? And we'll also start to see some of the applications of this. All right, so we have C and D here, and we want to find C dot D. So since it's in its component form, I'm going to multiply the x values together. So 4 times 2. Then I'm going to multiply the y components, so -6 times 5. And then the z components, so 9 times a -3. And we just basically add that all together. So you're going to have 8 minus 30 minus 27. That gives you a -49. So that's our dot product. It's a scalar. And what you should notice from what we did in the previous one, we expect theta, the angle between them, is going to be obtuse because we got a negative dot product. So let's actually find theta between them. So how do you find the angle between two vectors? Well, we're going to look at our first definition of the dot product, which was a product of the magnitudes times the cosine of the angle between them. And I can rearrange this so that I isolate cosine theta. So that's going to give me the dot product divided by the magnitudes. So we already know the dot product because we did that in the previous example. So what we need to do is find the magnitudes of these two vectors. So C is going to be 16 plus 36 plus 81. And that's going to give me the square root of 133. And then D, its magnitude, doing your Pythagorean theorem, is going to be 4 plus 25 plus 9. And so we get 29 plus 9, square root of 38. So putting that all together, we can find the angle. So we know that theta is going to be the inverse cosine of the dot product, which is -49, over the two magnitudes, 133, square root of 133, square root of 38. And it turns out that theta is going to equal about 134 degrees, which checks with it being obtuse and the dot product being negative. So there you see one of the applications. If you have two vectors and they come to you in component parts, you can actually then still find the angle between the two vectors, which will come in useful later on when we're looking to find the area of something. Okay, so this next example is where I would then set you guys free to go ahead and go through and do the process on your own. So if you want to pause the video and do this problem on your own, and then you can kind of fast forward to the result. Otherwise, I'm just going to kind of work it through for you. So we're looking to find the dot product and the angle between the vectors. So the first thing I'm going to do is find the dot product, since it's in component parts. -8 times 6 plus 4 times a -4, so -16, plus 1 times 5, and that is going to give me a -59. And then I'm going to go ahead and find the magnitude of each of those vectors. So this will be 64 plus 16 plus 1, which is 81. So this will be a nice 9. And vector S is going to be, let's see, we have 36 plus 16 plus 25, and that's going to give me square root of 77. So we have the dot product, which it asked for, so this was your R dot S. And to find the angle between them, we're going to just go ahead and do theta equals the inverse cosine. And we'll take the dot product, so -59. So once again, we expect the angle to end up being obtuse, over 9 times rad 77. So theta is approximately 138 degrees. Okay? Now, again, if you watch or look up the little PDF of the proof of the dot product, it'll show why these two forms actually equal each other. So it's not like I'm just pulling this out of thin air. It's actually taking two vectors and doing law cosines on them and then a bunch of substitution, and you can then see the relationship between them. So I'm not going to go through that on the video. I'll probably talk about it in class, and if it doesn't make sense, by all means, you can come in and ask me about it. But what I do want to show, this is another kind of justification of why we can do the inner product, which is the component parts. So remember, we have our unit vectors. So here's my I, my J, here's my K. And again, this works in 2 dimensions as well. We just happen to be doing it mostly in 3 dimensions. So if I were going to take the dot product of I with itself, realize that that would be taking the x components of I and I, which is 1, plus 0 plus 0, so that would give me 1. If I took the dot product of I with j, that would give me 1 times 0, plus 0 times 1, plus 0 times 0, that would give me 0, and I dotted with k would be 1 times 0, 0 times 0, 0 times 1, still give me 0. So notice I only get a result with the I dot I. So then we move on to, what if I did, well, we already did, it doesn't matter, it's very commutative since you're just taking products and sums. So I'm not going to do j dot I, but I will do j dot j. Let's see what happens. So the x components by themselves is 0 plus then 1 plus 0, so that would give me 1. And if I did j with k, that's going to be the x components would be 0, 1 times 0, another 0, plus 0 times 1, which is another 0. So notice we only get something when we do j dot j. And then the last one, since we've done k and I and k and j, is just going to be k dotted with k. So that's going to be a 0 plus a 0 plus 1, which gives me 1. So this is why the inner product works. All the others, everything else goes to 0, but when you multiply the x components together, the y components together, and the z components together, you get a scalar multiple of your 1, the result. okay? All right, so in conclusion, if you're doing a dot product, scalar product, inner product, all means the same thing. If the vectors come to you tail to tail and you know theta between them, this is the form that I would use. If the vectors come to you in component form, then I would do the inner product form, and that's when you're multiplying the x's together, the y's together, the z's together, and then sum them all together. And so in the end, these two forms actually equal each other, and they are a way of finding the angle between two vectors when they are tail to tail or when they come in component form. You can use it either way. So the next video is going to start to then talk about some of the applications, the scalar and vector projections that utilize the dot product. Okay, so this is just the end of this part.